It didn't. It didn't go well.
No, it did go well.
Oh, it did go.
Actually, had no issues except for at the end I didn't input like the five values because I was doing it in the actual textbook, so therefore it kept saying there's a scanner here because I only put in like two or three, but then I like put in five minutes.
Oh, I got you. I got you. And you this. You did all this with Edge.
No,
Because I think Edge is kind of equivalent to like using an abacus. Is it right? About the same?
I tried it for like 2 days and then I was like, no. Teaches them.
What didn't you like about it? Just because it's made by Microsoft?
That might have been part of it. I don't know.
I just broke out this horrible rash. Everything Microsoft just gives me that. It's the it's the whole security key thing.
If I would have given it more time, I might have grown to like it, but it was just things didn't necessarily make sense where they decided to put things. Maybe I don't know.
Okay. All right. So let's talk about the underbelly of arrays, since you've read stuff about arrays, and then we'll talk about parallel arrays, which you also read about. So let's start with this. So tell me, what's an array? Think about the features of an array. What are these guys? Go ahead. Okay, so collection of elements, collection of values.
Yeah.
Okay, so let's call it a variable type, capable of holding a collection of like type values. Okay, and this like type is kind of an important aspect of it. You can hold a bunch of integers or a bunch of doubles or a bunch of strings. You can't hold ints and doubles and chars all in the same array, at least not directly. We can use generic objects or something like that to pull it off, but they all have to be the same kind. Because when we define an array, if you look at the syntax for creating an array, it's type var name equals new type number of buckets. So that's the syntax for creating an array. So for example, we might say int AR is equal to new integer array 10. Something like that. So this is creating a variable named AR of type. Why don't we go ahead and make this correct? Number of buckets. So it's going to be type integer array, open close square brackets. The name of the variable is AR equals, and we have this guy, this new keyword, and then we're going to build it as an integer array with 10 buckets in it. That make sense? And actually, for right now, let me make it 3 buckets. That'll be easier for me to draw an example of. All right, so collection of like type data. Is there anything special about this variable, or is a variable a variable? It's a trick question. What's the definition of a variable? Go ahead. Okay, so it's a name that we associate with a value. So, and then we can use it multiple times if we'd like. We can also vary the value within it, hence variable, so we can change what it holds. But it's our association. So computers know how to store crap in memory, right? Well, human beings are not going to be real great at remembering memory addresses. It's like, oh yeah, where did I put that? I put that at 0x429AB hex memory address. We're not great at that, right? We've already seen our failures in real life. When I was a kid, I used to have to remember my friends' phone numbers. So really, you can only have like 3 or 4 friends, okay? Or you had to have the book where you wrote the stuff down, okay? And I think I probably asked this in maybe in 200 or something. How many of you actually know more than like one of your friends' phone numbers? Most of us do it by picture, right? Or we just tap on their name on our phone. Or now with like the new phones, we can just say call so-and-so. So we don't even have to know the number, right? I think like I would recognize my brother's or my mom's phone number if I saw it. but I bet you I would only get about 70% of the numbers right if I typed it. Something like that. I know my wife's number. I know my number. I think that might be it. I also know my phone number when I was a kid. That somehow is like cemented in there, right?
You gotta give it to people all the time. Oh,
Well, yeah, also you know your address. You're like, you know, like I remember the first address where I grew up, but several of the addresses that I lived in since that I've lived in for multiple years, I don't remember. Like my first apartment, I don't think I remember the address to that. Memory is a weird thing, isn't it? Yeah. But punchline is, human beings, we have our limits, right? So we like to word associate. Rather than remembering this crazy looking memory address over here, we want to have a nice, friendly looking variable name to associate. Like, where did I put that? Oh, I put that in AR. Okay, or I put that in my string, something like that. Okay, so variables hold values. All right. Now, when we talk about what are the types of values that we know how to hold? We've talked about our primitive types, right? What are the primitive types? Float. That's the guy that comes before short. Byte. No, no bit, just byte. And we're missing one more. Actually, we didn't have long, so we're still missing another one. We did. We didn't say Boolean. Yeah, Boolean. All right. So byte, short, int, long, float, double, char, Boolean. Make sense? A good way of remembering it, go through all the int types first. Then actually, I usually do char right after the int types, and then I do the small and large floating point value types, and then Boolean. And so the Boolean's like the period at the end of it. All right, so those are the variable types that we know how to store up to this point. We also talked about strings, right? So that's a new object type. That guy's not a primitive type, he's an object type who acts often like a primitive type, and we'll talk more about that as we start pulling some of these concepts together. So if I go into Eclipse here, I think I got the new Eclipse on here now. Neon's a new one?
Yep.
Ha! Nailed it. Did you actually watch the Packers game the other day?
Not really.
Yeah, it was. I don't. Even if you were trying to watch it, I don't think it was watchable. It was terrible.
Yeah, I don't understand anything about football.
You just wear the jersey.
Yeah.
Makes you feel like a Wisconsinite.
Yep.
It's just terrible. I mean, if there's a team you don't want to lose to, it's the Vikings. I don't have a problem with the Vikings. Actually, I don't even care if we win or lose. But if there's one team you don't want to lose to, it's them. Probably. I think there's less animosity in the Bears-Packers rivalry these days. It's muted. Yeah, so we lost to like basically a high school football team.
And they won the division, so last season. So
Yeah.
that hurts too.
Yeah. It's garbage. I don't think we want to lose to Detroit either. There seems to be like a budding rivalry there. The Bears rivalry is going away, the Detroit rivalry is growing, and the Vikings just never went away. When Favre played for the Vikings, that was difficult. It was a difficult time period for Packers fans. All right, so let me do this. Let's just get rid of this crap. All right, so if I go ahead and create an integer array, so int array AR is equal to a new int array, and we'll do that guy right there, 3. All right, and so I'll go ahead and let's fill that array up with a couple of values. So we'll do AR at bucket 0 is equal to 4, AR at bucket 1 is equal to 7, AR at bucket 2 is equal to 9. All right, and then when I do system.out.println, AR, what's going to display to the screen? You think 9? Okay. We have a 9, we have an error, we have nothing. Ah, finally a right answer. Finally right. So this guy's going to show weird looking memory address. All right, this guy right here. All right, so why is that? Let's give some rationale to that. Go ahead. Okay. So this guy right here plays a pretty big role in memory stuff. So I think we introduced him last year, but let's, in the book, talk about new keyword very much. So one thing I'm trying to do is, like, the book tends to teach things at the high level, and I want to teach it at the low level so you get kind of the full sandwich. All right, so let's talk about the new keyword. I usually refer to this. Anybody remember what I said last year? Pretty sure we talked about it in here. Call it our real estate agent.
They did.
Okay. So I like to think of this guy as like our real estate agent. The new keyword's job is to go out and find a place in memory for us to put something. Okay? So, you know, this is again getting to this idea that human beings don't like scary looking memory addresses. If you're a 325 student, you're going to get used to looking at scary looking memory addresses. That's what we're doing in there. Okay, but in here, we still pretend to be human. We're just the programmers, so we're just geeks, right? Computer organization people, there's just something wrong with them. They choose to be more at the hardware level. So, you know, this new keyword acts as the person who goes and finds us a plot of land for us to put our value that we want to store. We don't care what that memory address is as a human being, right? We just want to have the confidence that it's somewhere in memory that's not going to conflict with something else in memory. It's not going to get overwritten by something else. All right, so the new keyword returns a memory address. That's what this guy does. Specifically, it finds an area of memory large enough to hold the type of value that is being built. Make sense? All right, so it has to be large enough to hold the type of value that's being built. So what do I mean by value? Let's come back here. Generic syntax for a variable is type name equals value. All right, so this is the value portion of this. Now, what is the size of this value? So when I say int array 3, what am I creating? If you had to describe, you walk outside and you happen to see a 3-bucket integer array, how would you describe that? You're allowed to kind of connect it to a real life thing. Okay, so in this case, three values, right? Okay, so maybe you walked into Target and you were looking around the organization area or something like that. You find a little, desk organizer that has 3 little cubby holes in it, something like that, right? That's what a 3-bucket array might look like. Something you sit on your desk that has 3 little dividers to throw stuff in. Okay, now. That's what the guy looks like. So how much memory does that take up? What's the footprint of that guy? So if I go into Target and I find one of these desk organizers that has the three containers, 3 separators on it, how big is that? Let's say all the containers are equal size. How much space do I need on my desk for that guy? Okay, yeah, 3 times the size of one of the buckets. So in this case, it's 3 times the size of an int, right? And how big is an int? How many megs big is an int? I should have you give me the answer in megs. How many megs is an int? I'll take any size. What's the size of an integer? Okay, that's a horrible answer. Huh? That's what Google said. I had a slide up when I introduced all the primitive types. Remember when we talked about the size of all the different values? How big is a byte? A byte is 8 bits. Short is 16 bits. Int is 32 bits or 4 bytes. Okay, so 32 divided by 8 is 4. There's your whole 8 thing. Get it? Yeah. All right, so this guy holds 4 bytes or 32 bits. So how many total bytes or bits? Math will be harder to do bits. How many total bytes do I need to hold a 3-bucket integer array? 12, right? 4 times 3. The size of a single int times 3 of those. 12. Or if you want to do it in bits, it'll be 32 times, what's that, 96? 96 bits. All right, so those are the same number. 96 bits, 12 bytes, same exact value, just different representation. Okay, so that's how much memory I need. So when we ask the new keyword to go find us some land, go find us some memory in our system, something that we're not in charge of, because a whole bunch of stuff in our computer is competing for that memory, right? It even becomes weirder when we talk about the Java virtual machine. So we wrote a paper in here called about virtual machines, right? All right, so why would memory be weirder if we're talking about virtual machines as opposed to actual memory? When I request memory in the Java virtual machine, what am I actually doing? So there's our RAM. So 8 gigabytes, 16 gigabytes, whatever RAM you have. Then on top of that, we have the Java virtual machine. Now that guy is a program, right? Java virtual machine is an actual program. And that program, oh, the programs look different than memory, right? Programs are orange. Now what this program does it's going to grab a chunk of fake RAM. Well, it's real RAM, but from the virtual machine's perspective, it's fake RAM. So it's going to grab a piece of this actual memory right here and hold it hostage. And when we have a Java program that's requesting a portion of memory, what it's actually doing is it's asking the virtual machine, the Java virtual machine, to give it a chunk of memory out of its reserved memory space. The memory space that it's kind of held away from your 16 gigs. So maybe when your Java virtual machine launches, I don't know what the default value is these days for the amount of memory it goes ahead and reserves. My guess is maybe it's maybe 10 megabytes or something like that by default. Some relatively small value in the big scheme of things, but a relatively large value in terms of the number of things you can remember. So I mean, if you have 10 megabytes of memory, that's a lot of, so if, I asked you what's the size of an int in megabytes. So that's 4 divided by 1024, that's kilobytes divided by 1024, that's megabytes. So that's the size of a integer, which is 4 bytes in megabytes. 0.0000003814. I might have had an extra 0 in there, I'm not sure, but small, right? So if you have 10 of those, that's 2.6 million integers you can store in 10 megabytes. Starting to get a little context for 10 megabytes goes a long way if we're storing things like ints. All right, so if the Java virtual machine just went ahead and grabbed 10 megabytes of fake RAM to call it the Java virtual machine's RAM, for your Java programs, then that's what we're working with. Now, the Java virtual machine does take command line arguments. We've talked some about the command line here. So if I type in Java, which is the Java virtual machine, and I do a -H, it's going to show me a whole bunch of commands here for me when I run it to give me a larger address space or something like that. Let's see, is it like a -X, I think? Let's do print Java -X. Show all settings. Show settings. Okay, so this shows us we can set the heap size, which is being the memory size that we have. We can also set the maximum because the virtual machine will dynamically grow. You lose performance when you let it do that. But if we had a program that required a larger chunk of memory or doing some sort of scientific simulation or something like that, you can direct the Java virtual machine to claim a larger tract of land when it launches than its default value, whatever its default value is. I'm guessing at 10 megabytes, but it's going to be closer to 10 megabytes than it will be to your 16 gigabytes. All right, so some relatively small value for us. All right, so when we use the new keyword in Java, what we're actually doing is we're asking the virtual machine, a real estate agent who knows about the little town that is our virtual machine, to go and find us a plot of land that's big enough to hold this many of these guys. Make sense? Which in this case is 12 bytes. Now, more importantly, and let's go back to our example of Target. So I bought the little three bucket organizer thing, right? All right, so now how much space, remind me, do I need on my desk for that? 3 times the size of one of the buckets, right? So kind of like this amount of space. Well, can I just put a little bit of it here and a little bit of it here and a little bit over here? It's kind of all attached, isn't it? So I need to have that whole footprint, right? I need to find it clear, which is difficult often, after you've been using the desk for 15, 20 minutes after cleaning it, that footprint's hard to find, right? Okay, so I got to find the plot of land to put that guy, and now that's where my organizer goes. Right? Except I have a fan blowing from behind, so if the organizer doesn't have a back, things are going to blow out of it. It's the thing. But in any case, so for that organizer, we need the full space next to each other. We needed an empty plot of land on our desk that was large enough to hold the entire organizer. All right? Arrays are the same thing. So when I ask for a 3-bucket integer array, I need 12 bytes of memory right next to each other. Anybody remember the word that means memory next to each other from last semester? Contiguous. We talked about that, right? But I think it was pretty early in the semester when we were introducing programming concepts. So contiguous memory. Fancy way of saying memory in a row or next to each other. All right, so I'm holding 3 integers. Each one is 4 bytes in size. I can't just find 3 4-byte chunks somewhere in memory. I need to specifically find 3 4-byte chunks that live right next to each other in memory in order to build my array. That make sense? Now, a concept we'll talk about in the 300 course, which is a continuation of this course, but we focus more on something called data structures in there. And really, arrays would be our first data structure from a historical, I guess a historical concept. A data structure is a structure for holding data. All right, so whenever we think about computer programming, we're spending a lot of time storing stuff so that we can retrieve it later on, right? and we need different kinds of containers for storing stuff, just like in real life. You know, if you're storing leftovers, we probably go into our cabinet and find some Tupperware, or if you don't have Tupperware, then you do the let's make a Tupperware-like container out of foil or saran wrap, or we just use the plate and wrap it with something, right? You know, like a beach towel or, or something. You know, we get fairly creative. But just like in real life, we have containers that we put stuff in, right? And those containers come in different shapes or sizes depending on what we're storing. All right, so we need contiguous memory for an array. So when we ask the new keyword here to go and get us enough space to hold a value that's this large, it's going out and finding a plot of land that's 12 bytes big right next to each other. Make sense? All right, so why? Why does that memory need to be next to each other for arrays? This goes back to kind of how computers work. Let's come down here. Let's give ourselves our 3-byte array. All right, so those are our 3 buckets, right? That looks kind of like the organizer we found in Target. All right, now the new keyword is going to find us a place where we can put all those guys right next to each other, not a situation like that. Now, why is that? Why do you suspect that arrays require all the elements to be right next to each other? This gets back to something we saw a little bit ago. That is the output of this program. When I created an array of 3 buckets and then I printed out the value of this array, that is whatever value was stored inside of this variable. Remember last time I think we mentioned something that all variables resolve to their most local definition. The most local definition of AR is this guy right here. AR's value is this guy right here. So his value must be something that looks like this. When from our perspective, we put stuff in there that look like this, 4, 7, and 9. That's what we put into our array. Okay, that's what we threw at AR at bucket 0, AR at bucket 1, AR at bucket 2. But when we went out and printed out AR, as opposed to, I think you mentioned that it might print out a 9. AR at bucket 2, that's our 9. This is the value of AR. That's the actual value that our variable named AR currently holds. This is the value that AR at bucket 2 holds. Make sense? So why do so we're going to call this guy memory address. That's what he said, and it is. Although we saw our picture here, it's really a fake memory address, right? It's a Java memory address, and you can actually kind of see that from the output. This is an array of type integer at Java's memory address of 6D06D69C, which is a hexadecimal number. Okay? So would we prefer to memorize that or the word AR? We like AR, right? All right. So that's why we have variable names. So why do you suspect that this guy returns a memory address? What values did I put in here? 479. There's my 4. There's my 7. There's my 9. This is bucket 0. This is bucket 1. This is bucket 2. And I'm going to keep our memory addresses fairly simple here. So when we built an array, what really gets built is something like this. All right? The actual values live at various memory addresses. All right? So I decided that the base address of this was 100 rather than that guy. All right, so I picked a very simple hexadecimal number for my base address. We rolled the dice, got very lucky. Virtual machine gave us a very friendly base address of 100. So if I were to print out, so this whole thing is AR. AR's actual value, let's just do one of these guys. Is 100. That's the value stored in AR. Actually, let's make that guy green. That's the value there. All right, and I'm going to draw a little arrow. And we say that this guy points to a place in memory. Okay, points to a place in memory. So the value of AR is actually a memory address. In this case, by my example, is 100, which points to memory address 100, which happens to hold the value 4, which is a 32-bit or 4-byte integer value, signed integer value. Go ahead.
So they're just always the same. So the value of AR will always be the same as the first bucket.
It will be. Okay, so good observation. That's our first observation towards our answer. So AR at bucket 0 will always be the same memory address as the actual value of AR. All right, but what will print out there? Will this be the memory address or will this be the value at that memory address? Value at the memory address. All right, so this gives us our 4. With that in mind, what can you conclude that that special syntax does? What does that specifically tell us to do? Go ahead. Okay, resolve the value that lives at whatever memory address bucket 0 is. Don't tell me the base address. We're going to call this guy the base address of this array. Okay, the beginning of the array, the first place where the array starts. That's the base address. All right, so this is the base address of our array. AR at bucket 0 says go to, in this case, I'm going to say it at the high level, then we'll break it down. Go to the base address of AR and give me the actual value that lives there. Resolve the value. Make sense? All right, so AR at bucket 0, you says show me the value at memory address 100, right? AR at bucket 1 says show me the value at memory address 104. AR at bucket 2 says show me the value of whatever's at memory address 108. Okay? A math formula is happening over here. Can you figure out what that math formula is? Putting together all the pieces we've talked about? How do I get the value of 100 here using the 0? How do I get the value of the 104 using the 1? The 108 using the 2? What's that math formula? Go ahead. Okay, so in this case, 0 times 4. Why 4? 4 bytes. Yeah, it's an integer, so its size is 4 bytes. So, and then you said plus, what am I adding to it? 100. Why? That's the base address. So this is the base address plus 0 times 4. So the base address here is 100 plus, what's 0 times 4? 0. 100 plus 0 gives me 100. Give me the value there. This is 1 times 4. 1 times 4 is 4. Base address is 100. 100 plus 4 is 104. Give me the value there. This is 2. 2 times 4 is 8. Base address is 100. 100 plus 8 is 108. Give me the value there. Make sense? All right. Arrays require contiguous memory so that this math works. So that we can walk the various elements of an array. If I want 50 things in an array, I need to be able to get to element 38, for example, not by searching one element at a time, which would be very slow, but by going to the beginning of the array and then jumping in memory an offset of the position we want times the size of each of these elements. How many jumps do we need to make? Okay, if this is a 4-byte jump right here, and I need to make 38 of those, I'm gonna boom, right here. That's where the value lives. So it's fast. So we're doing math to get us to the actual place in memory. And in order to do that, we rely on all the elements of that array being stored in contiguous memory right next to each other. Make sense? So next semester, or possibly very late this semester, we're going to be talking about something called a linked list. Okay, so kind of our first, what's called a linear linked data structure. These guys work the opposite of this. So if you were to say, if you were to give me some perks, what do you think is good about this setup, this approach to arrays? What's good about that? We'll go back to our little Mario example here. I didn't have to jump like this. I did all the way to here. That's good. It's efficient. That's fast, right? I didn't have to jump 38 times. I just did one super jump to get to bucket 38. All right, so arrays are considered fast because we can mathematically calculate the exact place in memory where we need to go. We didn't need to go door to door to door to door to deliver the pizza, right? We went directly to the house because we knew how to find the house based off of its address. Now, what's bad about this? So speed is what's good. What's a negative of this then? Linked lists wouldn't exist if we didn't have to fix a problem with this. Okay, you lost one, you're kind of screwed. All right, give me an example.
So like if you lost the first one, you wouldn't know what to multiply. You wouldn't have the base address.
Okay, certainly base address is important. We have to protect that. But I guess if memory gets corrupted, we're kind of screwed anyways. So not a horrible thought. Not really the right answer, but you're thinking in terms of memory. So that's good. Base address is important, but I'll give you a hint. Linked list, that base address is important too. We need a starting point. Comes back to the real estate agent. So in this case, I need 12 bytes of memory next to each other. Is it possible? I mean, we're talking about a very small amount of memory here, but theoretically it's possible that we might have 12 bytes of memory free in RAM, or in Java's fake RAM, but not right next to each other. Is that a thing that could possibly happen? That we have 12 bytes available, but not contiguous. So arrays, A, might have a problem, or they're memory inefficient, would be the first part. We need to find chunks of land, chunks of memory next to each other in order to store these guys. All right? And the fact that they're next to each other is the very thing that makes them fast. But the fact that they have to be next to each other is also the very thing that might make them difficult to find a big enough plot of land for a large array. You know, we need to find a place to build a super Walmart. Okay, you just don't drop a super Walmart anywhere in a neighborhood. You got to find a plot of land big enough to hold that thing, right? All right, so same thing is true here. So there's our trade-off. Memory inefficient, but fast. Linked lists that we'll introduce later on this semester, early next semester, is going to be very memory efficient, because to store 3 integers, we only need 12 bytes somewhere in memory, in 4-byte chunks. We need 3 4-byte places in memory. But then they're also slow, because we don't just walk memory contiguously. We got to go to the base address, and then from there we say, okay, where's the next clue lead us? It leads us to this memory address up here. So I'll go there. Where's the next clue lead us from there? Oh, it says go down here. Now we got to bucket 2. That make sense? So that guy's slow, but memory efficient. So there's your trade-off. So it's not that arrays are bad or good. It's when is it the right tool for the job? And for the most part, arrays are pretty useful for us for many, many, many tasks. Now, there's one more downside to arrays that really will impact us relatively soon, that we've already kind of seen impacting us in the exercises we've been doing in the book. What constraint does an array put on us? Okay, fair enough. Not what I was looking for, but that is certainly a true statement. You can only store one kind of value in there, and to kind of work around that to some extent, we're gonna have to do some fancy stuff. So that's definitely a constraint that's on us. What's another constraint? Huh? Loops? What about them? Okay, so let's just assume it's wrong. Give me another constraint. Go ahead. That's it. One and done. Okay, if you choose to store 3 elements, that's how many elements you have. You have an array capable of holding 3 elements. And if you decide, oh, well, I really need to store 4, we can't just put an addition on. Why? Based on everything we've talked about today, why can't we just expand an array to be 1 bucket larger than it was before? Go ahead.
You've already allocated the contiguous memory size, and you can't necessarily depend on being able to add more.
Yeah, that's the right word. We can't depend on it. Because when we sent our real estate agent out to find us 12 bytes, plot of land big enough to hold 3 integers in a row, okay, that real estate agent didn't pay attention to whether there was an extra little plot of land next to it just in case, right? They gave us the first place they can find, or the best place they can find, you know, whatever algorithm the real estate agent used to figure out the memory they were going to give you. They found the place that it would fit, okay? Something like that. So when they came back with the memory address, they said, look, this is your space. No more, no less. This is all reserved for you. You can't just put another bucket on the end of it. Now, in reality, you might be able to. You know, that memory might be available, but I'm not guaranteeing it to you. So that's not your land. So just like in my house, I can't just go build a shed in my neighbor's yard. Well, he's not using it for anything, right? So that would be kind of funny. I'm looking for ways to get back at my neighbors. I have problems with those people. They won't keep their dog on a leash. They have a big dog. My wife's afraid of dogs. The dog seems friendly enough, but she carries pepper spray to the mailbox because she's afraid she's going to get attacked by their dog. That doesn't seem reasonable, does it? So you think you go up and ask somebody nicely to say, oh, can you keep your dog on a leash? They would do it. They do it for 2 days. I've had to call the cops on these people. They still don't do it. So I should build a shed in their yard. I think we just got a solution to this. My wife didn't like some of my crazy solutions. Like I was going to have a fleet of drones that I was going to have like laser pointers on them that would target their dog. I wasn't going to actually shoot the dog, but they didn't know that. So keep your dog in a leash and out of my yard, because the dog would come over. Well, maybe, yeah. But I mean, the dog would be over in our yard. Like we have pictures of the dog like by our mailbox. And like I said, the dog seems friendly enough. I'm not afraid of dogs. It seems like a nice enough dog. My wife's terrified of them. All dogs, little, big, doesn't matter. Just terrified. Like how some people are with snakes. She likes snakes better than dogs. Yeah, but that doesn't work because, I mean, the dog fences, the electrical ones, require the dog to wear a collar. So, like, what, am I supposed to go over and start sticking clothes in their dog?
No, the one in Lost, if you pass it, and if you go through the fence,
Oh, it's like a special electric fence. Yeah, so I don't really want to hurt their dog. I mean, I just want them to keep their dog on a leash. So, I mean, it's not the dog's fault. Dog, he's just being a dog, right? You put a dog out in the yard, you don't have him on a leash. The dog's going to do what dogs do. They run around. Isn't that how people cheated at Pokemon Go? I think they just strapped the phone onto a dog and went and had the dog hatch their eggs for them. Dogs are great at that. So, yeah, I don't like those people. Yeah, so we can't just build things in our neighbor's yard, whether the spot is available or not. All right? So, punchline. When we ask for memory from the new keyword, where's my new keyword? Nailed it. All right, when we ask for memory from the new keyword, that guy's going to go out and get us the amount of memory that we requested. No more, no less. Okay? So if we want to have one more bucket, what do we have to do? So we come in here. I have a 3-bucket array. I've put 3 values in that guy. But now I want to have I want to be able to store a 4th value. What do I need to do? Well, okay, this guy already exists. Yeah, certainly I could just come up here and say, well, done. Recompile, now put your 4th number in there. No problem. But this guy already exists. So I already went to, Target. I came home with my organizer for my desk with 3 elements in it, 3 buckets in it. And I decided, you know what? It would be nice if this thing had a 4th. What do I got to do? New array. Yeah, I got to go back to Target and get the bigger model, right? The 4-bucket one. So I'm going to come here, and we're going to create an in array AR2, and this guy's going to be a new in array of size 4. All right, and just to show you here, we'll print out AR and AR2, and we'll see that these guys are different memory addresses. Okay, so 2 different memory addresses, because they're in different places in memory, because one of them was capable of holding 3 elements, the other one was capable of holding 4 elements. So this is my smaller desk organizer, this is my larger desk organizer. All right, and we can't tell that by the memory address, but we just happen to know that I printed out the small one first and then the larger one. Okay, now I might want to get all the elements from my smaller one into my larger one. I want to copy all those elements. How would I do that? What code could I write that would copy all the elements from AR into AR2? We might be inclined to do something like this. AR2 is equal to AR, right? Well, I'll just move AR into AR2. This is the assignment operator, right? The assignment operator assigns whatever the value on the right-hand side is into the variable on the left-hand side. What is the value of AR. Memory address, okay? And this guy's a variable name. So I'm assigning this memory address into this variable. What did I just do when I do that? What happened? Well, I didn't really chop off one of my sections. Here, we'll do the output. Remember, I'm printing out the value of AR and AR2 here, right? Now they're the same. What happened? What did I do? Just keep this simple. So there's AR and AR2 after I create them, right? Now when I set AR2 equal to AR, what happened here? AR2 has its value replaced with whatever AR's value is, which effectively means that this guy now points there. What happened? Can I get to that stuff anymore? I lost it. I abandoned it. I built the shed in my neighbor's yard and then forgot it existed. Okay? Looked the other way. Never going back. So now we have let this guy lose all pointers to it. So initially, we have this thing called a pointer count. All right, so a memory address has a pointer count. So this memory address 200 had a pointer count of 1. There was one variable that pointed to it. One street that let us get to that place. That make sense? And as soon as we change the value of AR2 to point to someplace else, that pointer count dropped from 1 to 0. And when the pointer count for something is 0, that effectively means there is no way to get to this value. Which means what? If I have some stuff stored in memory and there's no way for me to get to that place in memory programmatically, meaning you could write an assembly program or something like that that literally just goes to that place in memory. If you would have to know where it was, but then you'd have a higher pointer count, right? I suppose you could just walk memory 4 bytes at a time and just see what you find. And then it's like a wild goose chase. But once something's pointer count is down to 0, which means there's no roads that go there, what does that tell us? What can we do with that memory? Is this useful to anybody right now? Now, who gave us this memory? The computer through the real estate agent, right? The new keyword. So the new keyword went and found us this memory. Okay? And what did we do to thank them? We abandoned it. We abandoned this memory. So there's no way to get to it now. What does that mean? What can we do with this now? Go ahead. Use it for something else. This no longer needs to be reserved for us because we abandoned it. So we let whoever know, right? The real estate agent, this plot of land that the real estate agent gave it to us once now needs to be flagged as available again. That the real estate agent could give it to somebody else or give it to us for our next variable, whatever. Something like that. Because we're not using it. And we know we're not using it because its pointer count is 0. That Make sense? Nothing points to this anymore. These kinds of values, variables that are capable of holding a memory address, for this reason, we call them pointers. Pointer is a primitive type. Let's leave primitive type out. It's just called variable type that is capable of holding a memory address. Okay, that's what a pointer is. Now, there's a pretty good chance, I haven't looked, that your book will never mention pointers. Most Java textbooks never mention pointers. In fact, it's pretty common for Java textbooks to reference that pointers don't exist in Java. Remember when we had our picture that showed where Java lives in the lineage? This guy? Java's right here, which is, let's call it the upgrade to C++, which was the upgrade to C. So this was a procedural programming language. We upgraded to an object-oriented programming language, and we upgraded from there to still an object-oriented programming language with some fixes. The fixes mainly came in the realm of memory and security. Java runs inside of a virtual machine. So bad things that happen only happen within that virtual machine. That make sense? If you're a Mac user and you're emulating or running a virtual machine of Windows, and that virtual machine gets a virus, does your Mac computer get hurt? No. You probably just grab your original image. A lot of companies do this. If you've worked, any of you worked in an internship that used virtual terminals instead of an actual computer, you might have been on an actual computer, but the installation of Windows that you would use even in Windows was a virtual machine. And why is that? Well, because if something happens to your computer, your productivity time, you lose 10 minutes. They just reload your the base template before the virus happened, and boom, you have that, and all your files were on shared drives and stuff like that, so you haven't lost anything. Good as new. Instead of spending time running virus detection and stuff like that, the quickest solution is just, we'll just reinstall the OS. Well, reinstalling an OS and reinstalling all the software and stuff like that normally takes a decent chunk of time, right? Well, with a virtual machine, it takes 5 minutes. Let's just reload it on the server. There, boom. However long it takes them to copy the 1.2 gigabyte file over or something like that, that is your installation with all your it's probably more like an 8 gigabyte file over the local network or something. All right, but in any case, Java did a lot for us to protect us from memory misuse in C++. So over the last couple of minutes, we've been talking about how we couldn't just add another bucket to the end of our array. In C++, we kind of could have. Nothing blocked us from just jumping right here. It's like, hey, I have this memory address. Why can't I just go to this memory address? What keeps me from building that shed in my neighbor's yard? Nothing really. I mean, I might get in trouble, right? I might overwrite some memory or get shot at or something, Bad things, there could be consequences, but I can still do it. Java, we can't even do it. We're protected. We're walled in. Okay, so Java protects us from memory. And the way it's done that is it's taken away our ability to manipulate memory. Now, what I've defined here is that the definition of a pointer is a variable type that is capable of holding a memory address. Now, we know that pointers exist in Java. We're looking at them right there. That makes sense? What we can't do in Java is we can't manipulate that memory. We can't go to this memory address and add 4 bytes to it and then look at that new place in memory. Java protects us from being able to do that. Okay? Which, let's say most of the time is helpful. I'm sure some of you ran into it in your homework assignment whenever you walked off the end of an array. You tried to access bucket 4 in a 3-bucket array or something like that. What error message would you get? one of the skills we're going to be learning from doing all this stuff, well, you hopefully are already down the path of learning this, is debugging, right? So every single one of you wrote all your code the first time, no errors? Probably there's a common error that I bet many of you saw. The error was array index out of bounds. How many of you saw that? Several of you. So array index out of bounds, that error, the very first thing it should raise for you is a red flag that says, oh, I've walked off the end of an array or of a string. You'll get that same error both ways. Okay? I've either tried to access an element that's off the end of the array, or probably less commonly, I've accessed an element that's before the beginning of the array. You know, like you tried to access bucket -4 or something of an array of any size. First bucket is 0. Anything left of 0 is going to be bad news. Okay, but sometimes, especially as we're getting used to it, you might assume that the last legal bucket in a 4-element array is at position 4, when it's actually at position 3. 4-element array has legal positions 0, 1, 2, and 3. And now we know why. Why is the first element at 0? Why did they just arbitrarily choose 0 instead of 1? For this math. Right there. That math won't work. Or the math gets a little bit weirder, right? You can do 1 minus 1 times 4 to get you to the right memory address. So I guess you can make the formula a little bit different. But bottom line is, until we get used to that, it's going to be fairly common for us to accidentally walk off the end of an array. Other reasons we might walk off the end of the array is we might have the wrong Boolean expression in our loop, right? Instead of going less than 4, we did less than or equal to 4. Something like that. So we go through one extra time, then it screams at us that last time. Okay? Evidence that that might be what's going on is if you're printing each time through the loop, you see a whole bunch of print statements and then boom, an error. That meant you probably went through an extra time. Make sense? So these are some skills you'll get as you continue to practice this stuff. All right, so now when the pointer count goes to 0, when we no longer have anything actually pointing at this array, and we've effectively said, take it back. Java has something built into it called automatic garbage collection. Okay? Again, we're thinking about Java in terms of what it means for it to be an upgrade to C++. So one thing it did is it took away our ability to manipulate memory, kind of keeping us from making our computers crash. Because what keeps us from just walking past the end of our array and overwriting portions of the operating system and stuff like that in memory, which then you have to reboot your machine to let it load back into memory so you can undo what you just did. So Java protects us from ourselves. Most of the time this is beneficial. Every now and then, a good Samaritan could take advantage of memory manipulation to solve a very specific problem, something like that. And you've kind of taken that weapon away from them in Java. That doesn't mean they can't do it another way. They just couldn't do it the short circuit way or something like that you maybe would have been able to pull off in C++. All right, but a majority of the time it's for the best. So they've also introduced this idea of automatic garbage collection. In languages like C and C++, C++ specifically, that new keyword existed. Okay, so in C++ we had the new keyword. Let's come back here. Memory, well, let's call it the real estate agent. Real estate agent has gone by several names through the history. In C, it was called malloc, memory allocate. Okay, so if I wanted enough memory for a 4-byte array, I would say malloc 4 times size of it, like that. And that would find me a chunk of memory capable of holding 12 or 16 bytes. All right, so real estate agent in C was malloc. C++ was new. Java is new. C# is new. Objective-C is just alloc. Swift just took it away. Still there, but why type new if it's always going to return a memory address? So they just took the word out. It's a silent give me memory. All right, something like that. That's kind of a telltale sign of Swift, is they've removed a lot of extraneous typing from the language. In many cases, it's an improvement, in my opinion. But in some cases, they've removed things that I feel are structurally important to the code. Like, fine, you didn't have to type it, but you know what? You really should type it. You know, sometimes the opening and closing parentheses on an if statement kind of designate, like, this is where my Boolean expression goes inside of the parentheses. To say you don't need those parentheses, it's fine, but now you kind of lost your little container for throwing your Boolean expression in. Did we really save that much? Java's on my list right now anyways. This last week, or not Java, I'm sorry, Apple's on my list from a technology perspective. This last week, they released 3 big things. They released Xcode 8, so they're new, basically their new Eclipse. iOS 10, their new mobile app, software, mobile operating system. And to add insult to injury, they decided, let's just revamp Swift. So they released Swift 3, which effectively breaks most existing projects. Now, fine, there might be some things that are improvements to it, but as an example, they changed capitalization in some things. So, like, instead of it being for like a color, instead of it being dot white with a capital W, it's now dot white with a lowercase w. So every single time you use the color white in your entire program, you now have to go through and change the syntax. Just because they decided that the lowercase w was aesthetically more pleasing. Good rule of thumb as technologists, don't release more than one major thing in 1 week. 2 is a bad idea. 3 is criminal. That should not have happened. All right, so in any case, pointers are our variables that hold those memory addresses. And we have this idea of automatic garbage collection, which was introduced in Java, that says, we're going to go ahead and think of it like a garbage truck that drives around memory looking for abandoned memory locations. That is, memory locations that have a pointer count of 0. If it's abandoned, go ahead and reclaim it. Reclaiming it could mean several different things. Really what it means is just let the operating system know that nobody currently has a claim to this land. You don't have to zero out the values there if you don't want to. You know, which sometimes then you'll come in and get a new value and like, oh, well, there's something already here. So who cares? Java does happen to zero it out. So there's a default value for an integer because it gives you a base value, but you should never rely on that. If you want it to have an initial value, put an initial value in there. So this is automatically release memory back to the OS. In previous languages like C++, there was a command called delete. In C, it was dealloc, to deallocate that memory address, give it back. So you used to have to manually clean up your mess. Java, you don't have to manually clean up your mess. But with that comes a level of additional overhead. Okay? That additional overhead is what? That now I have to spend processor power having this garbage truck drive around. All right? So, for Thursday, from your book, there's a second programming problem on, what, chapter 4?
5.
5? Yeah. The soccer one?
Soccer.
Yep. So complete 5.13, and I'll put a Dropbox up and submit that to Blackboard. So how many people were not able to get their project submitted to Blackboard? Okay, so email it to you. You already sent me yours. Email me yours. Okay, so but try to get it up there sometime today if you can. It won't be the end of the world, but it's easier if I can grade it in there. Otherwise, it screws up the grade book. But anyways, all right. So I will see everybody on Thursday. Remember, today is the student, faculty, staff Bible study. Starts at noon. Just go to the cafeteria, get free lunch, God and grub. So we usually go down to 11:30 and start eating, and then we just take it down to the Lakeshore room. So if you're interested, we have a CS table.